Hello, I'm going to tell you about my project to make E smart again after removing some limiting features. E is a saturation-based automated theorem prover that tries to prove a conjecture from premises by refutation. It does this by throwing the negated conjecture and premises into the unprocessed clause set, and in each step of the given clause loop, a clause is chosen, and all valid inferences with the currently processed clauses are done. Then G is added to the processed clause set, and the process is repeated with newly generated clauses. E's strategies consist primarily of clause evaluation functions, term ordering, and literal selection. Clause evaluation functions consist of priority functions, such as keeping everything in one priority queue or processing all unit clauses before other clauses, and wait functions, which order the clauses in the queues by wait or just first in, first out. So this is a classic strategy, which weights two clause evaluation functions by frequency of use. This is a strong strategy that was learned by machine learning called E1. The E2 is another such machine learned strategy. And now term orderings essentially determine the rewrite order in E and contribute to the theoretical completeness of the proof search and can prevent cycles. For example, given x plus 0 equals 0, we can rewrite x plus 0 to x. However, we cannot do the other order, as it is writing from a smaller term to a larger term. Our strategies generally use the Knuth-Bendix ordering. Literal selection limits clause resolution in E, which is like modus ponens, which this limits redundancy and also contributes to the theoretical completeness. For example, giving A or B or C and not A and not B, there are two routes to deduce C, and literal selection guarantees that only one of these is going to be chosen. So ENIGMA is the statistical learning suite that our research group has been using, and here I use XGBoost, and this we learn from the selected given clauses, which are either used in the proof or not. They're negative, and these are mapped into vectors, and we get a model that predicts whether the clause and conjecture pairs are positive or negative. Roughly speaking, clauses are mapped to vectors via the tree representation of the clause, via various features such as tree walks of size 3 like this, which then gets counted up and later hashed into 16,000 buckets or something. The end result is 100 or 200 decision trees like this, which go from clause features to positive or negative as a prediction. The data set we use is usually the Mizar mathematical library of around 58,000 theorems with premises already selected. And previous ENIGMA results are that our strong strategies prove around 14,000 problems, whereas ENIGMA has a 70% improvement of 25,000 problems after many loops of training. The research question here is, can ENIGMA guide E without its strategies? So first I make E stupid, and then I try to learn. To make E stupid, I replace the KBO ordering with a structural identity relation that judges almost all terms as incomparable and incidentally disables term rewriting in E. And literal selection is also disabled, so E is free to do as many inferences as it needs to. And only this basic strategy is used, rather than a more sophisticated one. ENIGMA training is done in loops where E is run with the basic strategy, a model is trained, and then E is run with the model and the basic strategy, and then it's run in solo mode, only with the model. And this is just repeated. The main hyperparameters are the number of loops of training, the number of trees per loop, and the depth of the trees. The first test uses constant parameters such as trees of depth 16 for 100 trees of depth 16 for 15 loops, and so long as the trees are sufficiently deep, this performs pretty well compared to the baseline. In the next test, the trees and/or the number of trees and/or the depth are gradually increased as each loop. Initially, this doesn't do much better than the constant parameters. However, beyond loop 8, some of the methods do significantly better than constant parameters, so increasing the depth of the trees helps a lot, which is not surprising. In a case where we're learning from scratch, using as much data as possible is probably very useful. However, training can take at least half a day, so these experiments are less structured. Experiment 5 is very messy, as I tried just doing as many loops as possible and other hacks to see how far ENIGMA could go without term ordering or literal selection, and it does surpass our strong strategy. E3 here uses strategy Inc. 3 here, and it has no additional help. So it does quite well initially and then plateaus, possibly due to overfitting. Experiment 4 is like 3, but gets the data from E1 and E2 in addition to the E0 data initially. So it has some boosting data, and that shows that a simple protocol can lead to performance on par with these strong strategies. And in experiment 5, along with other things in the appendix of my paper, data from a strong ENIGMA model is also fed in initially. So it's quite a big boost, but it can really leverage it. In conclusion, ENIGMA can learn to guide E without its strategies, and even with the E0 data alone gets 150% increase. So it can do it, but term ordering and literal selection are still very helpful. And some questions are, can this gap be bridged, perhaps by the neurally guided ENIGMA, and perhaps relaxing term ordering will help to combine strategies. So we should probably keep these experiments in mind as we further machine learned inference guidance on E. Thank you, and if you have any questions, please ask.